When we think about the geometry of objects, our standard human intuition relies on a simple binary. An object is either broken into separate pieces, or it forms one solid continuous whole, merging together into a single connected space. But in the rigorous environment of point-set topology, relying on visual assumptions is a liability. As mathematical spaces become more complex, our everyday understanding of what constitutes one piece completely shatters. To understand exactly how this intuition fails, we can look to James R. Munkres' foundational textbook on the subject. Today, we are going to examine a topological space that presents a precise mathematical paradox, a shape that is strictly defined as entirely connected, yet is completely impossible to travel across. This animated graph plots the first component of this paradox, known as the topologist's sine curve. The equation is y equals the sine of 1 over x, evaluated for all values of x strictly greater than 0. As x approaches 0, the curve oscillates infinitely. To complete the space, we add a distinct vertical line segment exactly on the y-axis, stretching from y equals -1 to y equals +1. This union formally defines the space as the closure of the curve. Mathematically, this entire combined shape exists as exactly one connected component. However, it requires two completely separate path components to describe it. Resolving this contradiction requires discarding what our eyes tell us and instead relying on axiomatic definitions to strictly partition spaces. We have to dive into Chapter 3. How do topologists rigorously break an abstract space into its natural maximal pieces? They rely on an equivalence relation, a strict mathematical rule determining if any two distinct points belong to the exact same piece of a given space. We define 2 points, x and y, as equivalent if a connected subspace expands to contain both. By combining all overlapping connected subspaces for every equivalent point, the boundaries expand until they capture the largest possible connected piece of the geometry. The resulting maximal equivalence classes derived from this exact process are defined as components of the space. As we see in Theorem 25.1 of Munkres, these components are perfectly disjoint from one another, and their union seamlessly forms the entirety of the space X. But we can apply a second, much stricter equivalence relation. What happens if we demand that a literal, continuous route must exist between the points? Here, a solid continuous line shows this stricter relation. Points are equivalent only if there is a continuous map, a path, joining them from point A to point B. The equivalence classes generated exclusively by this continuous map relation are defined as path components. Theorem 25.2 establishes that, similar to standard components, path components are disjoint subspaces whose union makes up the whole space. Treating components and path components as synonyms, however, will completely obscure the true behavior of complex geometry. Munkres highlights this exact divergence in example 2, which is explicitly designed to shatter the assumption that components and path components are always the same sets. Looking at the topologist's sine curve, we see 2 subsets, the blue oscillating curve and the red vertical interval. Because the blue curve approaches the red line infinitely, the closure of the set is connected. The entire space forms exactly one component. The path property is entirely different. Any path starting on the red line and attempting to reach the blue curve inherently breaks continuity, shattering as it hits the empty space between the y-axis and the infinite oscillations. The mathematical reality is absolute. The space contains exactly one component, but 2 completely separate path components. The topological mechanism responsible for this divergence is the distinction between global properties and local behavior, specifically a condition known as local connectedness. This visualization demonstrates local connectedness at a specific point. For a space to be locally connected there, every open neighborhood surrounding that point must contain a connected subneighborhood. We can apply this local connectedness test to the origin of the topologist's sine curve to see exactly where its structure breaks down. In this extreme zoom, an arbitrarily small open ball drawn around the red vertical interval captures an infinite number of disconnected parallel vertical slices of the blue sine wave. They never connect within the circle, failing the local connectedness test entirely. A topological space can possess a property globally, like being connected, while entirely lacking it locally. That local failure is how pathological paradoxes survive. If these definitions can diverge so wildly, under what specific mathematical conditions do components and path components finally align? The alignment relies on one required condition: local path connectedness. Conceptually, local path connectedness means that arbitrarily small, path-connected building blocks exist uniformly everywhere across the space, allowing no unbridgeable gaps. Munkres formalizes the resolution to this tension in theorem 25.5. The theorem provides a powerful guarantee. If a topological space is locally path-connected, then its components and its path components are guaranteed to be the exact same sets. In a standard geometric space like this open disk, the condition holds. The properties align perfectly, and the component is the path component. The sine curve's failure to be locally path-connected at the origin is the only reason its sets were allowed to fracture. Theorem 25.5 grants topologists a reliable analytical test to classify spaces accurately, without relying on visual assumptions. Mastering advanced topology requires permanently separating human geometric intuition from the rigors of axiomatic proofs. By isolating global components, continuous paths, and local neighborhoods, mathematicians gain the exact tools